Good afternoon, everybody. How are we all going today?
I'm Paul. How are you?
I'm good. How are you?
I'm fine, thank you.
That's good to hear. How's everyone else?
Yeah, I'm good.
That's good to hear. Um, okay, so what we're going to be doing today is just working through some exercises. I think Chris has posted them on Canvas, and they're basically about estimation. So we'll be looking at some method of moments estimation, as well as some continuing with some maximum likelihood estimation. Okay. So I think the exercises are all fairly self-explanatory. So let me just set this up and bring you guys over to my board here real quick. Okie dokie, and we'll get started on these exercises. Now, before we get started, I did want to remind everybody that we do have an 11-week semester. So what that means is that next week is going to be our last class, okay, before we all go on and do our separate things, all right? And if you have any questions about the exam or you wanted to know anything about sort of how to prepare for it in particular, feel free to let me know next week, okay? And I'll be more than happy to have a chat about that with you, okay? Alrighty, let's get started here. I'm trying to figure out why I can't see this. All right, so hopefully this works. If you just give me a second here. There we go. All right, fantastic. Okay. All right, hopefully you should all be able to see that. If you have any issues, let me know and I'll try and fix it up. All right. But I think that seems to be working for me. So let's get started, guys. Okay. So this first question first problem that we're going to be working through here is we're told, okay, that we have the following setup, okay. So we're told that we have Y coming from a simple random sample or an IID sample, okay, from this distribution right here, where f of yi is given by this following distribution, okay, theta plus 1 times y to theta, for y is between 0 and 1, not inclusive, okay, and this theta is greater than -1, okay, and 0 otherwise, okay. All right. You're asked to find an estimator for theta by the method of moments and to show that the estimator is consistent. Okay, now we're asked whether this negative sum of log of yi is, it can be obtained from the factorization criteria, so whether it's sufficient and what is the implication for this. Okay, I'll talk about that in just a second, but first of all, right, the idea behind the method of moments, right, okay, is that if we have some estimate, okay, let's say y bar, right, we can use that to estimate the expectation of y, okay, which will then allow us to estimate the theta, okay. So that's the idea behind the method of moments, right? We want to find what is this theta as a function of the expectation, and then we can replace that expectation with the sample estimate, and that gives us our method of moments estimate, okay? So first of all, let's have a think about what the expectation of y actually is, right? So it'll be the integral from 0 to 1 of y, f of y, dy, okay? So the integral from 0 to 1 of theta plus 1, y to the theta times y, so that'll be plus 1, dy as follows, okay? And this is fairly easy to integrate, okay? This is going to be y to the theta plus 2, and you divide by the new power, so theta plus 1 divided by theta plus 2. Oops. And we evaluate this from y is equal to 0 to 1, okay? All right, so of course, I think we can all agree that this is equal to theta plus 1 over theta plus 2, okay? So therefore, we can say that expectation of y, which let's just call mu to make it easier to write, is theta plus 1 over theta plus 2. Okay, so what we want to do here is, let me just do some quick calculation, all right, because I can't do this in my head, and then I'll tell you what theta is in terms of mu. Okay, so you might have something like this. Plus 2 mu is equal to theta plus 1. So therefore, we want theta in terms of mu. So theta mu minus 1 is equal to 1 minus 2 mu. So therefore, we can say, right, that theta is equal to 1 minus 2 mu over mu minus 1, right? So that's just from this sort of draft calculation over here, right? Okay. So what we can do now is using the method of moments, okay, we replace mu, which is the expected value of y, with y bar, okay? So therefore we can say that theta hat, using the method of moments, is equal to 1 minus 2 y bar over y bar minus 1, okay? All right. Where, of course, I think we all know that y bar is the sample mean, right? Okay. All right. Now, this is consistent, okay? Of course. Now, why is this consistent? Because the p-lim of y bar is equal to mu, okay? So therefore, the p-lim of f of y bar is equal to f of mu, right? And of course, that's going to imply, because this is a function of y bar, okay, that this method moments estimate is going to be consistent, all right? Okay. Let me see if I can get this to be better quality for you guys. I think it's fine, but it'd be nice if I can get this to look a little bit nicer, huh? How about I do this? Is that any better? Probably not. Okay, we'll have to live with it. All right, but I think it's still quite clear what I'm writing, so that's okay. All right. Now, the next part of the question is asking us whether this right here is a sufficient statistic. Okay, is negative log of y, sum of log of y, a sufficient statistic? Okay, and the answer is clearly no. Okay, why is it not a sufficient statistic? Well, intuitively, we cannot find. Let me write this a different way. Okay, intuitively, theta hat method of moments is a function of this, right? Okay. So therefore, hang on. Let me think about this for a second. Is the estimator function? Oh, this is a sufficient statistic. Sorry. That's why this doesn't make sense. Yes, this is a sufficient statistic. Okay. Now, intuitively, this theta hat method of moments is a function of the sum of yi. So therefore, we cannot represent theta hat method of moments as a function of this guy right here, okay, the log of yi, because there is no way to calculate or to represent the sum of yi from the sum of the log of yi. Okay, so this means that by, what's the theorem? I think it's Lehmann-Scheffer, right? It must be the case that since theta hat is not a function of the sufficient statistic, it cannot be, the best unbiased estimator. Okay, that's the implication of that. All right. Okay. So hopefully that's all good. All right. Okay. So that's question 1. Fantastic. Okay. Question 2 is straightforward. So suppose that y denotes a simple random sample from the normal distribution, mean 0, variance sigma squared. Find the method of moments, estimator of sigma squared. You can all do that, right? I think that this one is quite straightforward. So let me just briefly talk about this. Just one line is enough probably. And then we can move on to 3, which I think is a more interesting question. It's a gamma, okay? So here we have y, okay, being drawn from a normal 0 sigma squared. And you're asked for what is sigma hat squared method of moments, right? That's the question, okay? Well, here we can see that the variance of y, okay, is equal to, well, e of y squared minus e of y all squared. But because the mean is 0, this is equal to e of y squared, okay? So therefore, we can say that sigma hat squared is equal to mu hat squared, mu 2 hat, which is going to be 1 on n times the sum of yi squared, okay? And that's your method of moments estimator. All right. Okay. So I think that's hopefully not too difficult to follow there. All right. So I think we can move along and have a look at the next problem here, which is question 3. Now this one's going to be a maximum likelihood question. All right. So let's have a look at question 3 here. Okay. So we have y being a simple random sample from a gamma distribution, and we're asked to find what is the maximum likelihood estimate of theta. Okay. Okay. So let's write down our problem. So what we have here in this one is something like this. Okay. We have yi is a simple random sample from this distribution here. Okay. Gamma distribution has 2 parameters, alpha and theta, and it's equal to.
Sorry, Paul. Are you
Yep.
writing off the screen at the moment?
Am I? Let me just fix that up real quick. Does that work?
Yeah, I think that's a little bit better now.
Yep.
Thank
Okay.
you.
All right. Gamma of alpha, and then it's theta to the power of alpha, y to the alpha minus 1, exponential of minus y on theta. Okay, for y is greater than 0, theta has to also be positive, okay, and it's 0 otherwise, right? Okay, so that's your typical gamma distribution, okay, and we want to find, find the maximum likelihood estimate, MLE, of theta, okay, which we'll call theta hat, MLE, okay? All right, so what's the likelihood function here? The likelihood function of theta, okay, is going to be given by the product of the distribution of the y's. Okay, so that's going to be given by the following, the product of 1 over gamma alpha, theta alpha, y to the alpha minus 1, I should say yi, exponential of minus yi over theta, as follows, okay? So what we can do here is to simplify this a little bit. We can take this guy out front here. So we have 1 over gamma alpha, theta alpha to the power of n, don't we? Yep. Okay, and then we have here the product of yi to the alpha minus 1, like so. And then this is a exponential, so if we take that inside, this becomes a sum. And this is minus 1 over theta sum of yi, right? I think that's all correct. Okay, so what we're going to do now is we're going to take the log of the likelihood, all right? And if we take the log of the likelihood, then I think this problem should fall apart fairly easily. So the log of the likelihood, this should be theta and also alpha as well, I suppose, right? Okay, let me fix that up here as well. Okay, let's see what happens when we take the log. So we have n or minus n times the log of this entire thing. That's not important because that's a constant. This is a product. So this product is going to become a sum when we take the log. So it's going to be plus alpha minus 1 times the sum of the log of yi because the power comes down. Okay. And then the exponential will disappear. Okay. Fantastic. All right. So therefore, we now have the following first order conditions. Okay. So we take the derivative of the log likelihood with respect to theta. What do we get? Well, we simply get No, I see a problem. Okay, give me a second here. I think I need to do one more simplification step here because I was lying. This is not a constant with respect to theta because it's not linear. So we have minus n times the log of gamma of alpha. Okay, then we have minus n alpha, the log of theta. Okay, then plus all this stuff here. Okay, so we can actually see here that we have this first of all. So this will be minus n alpha over theta. Okay, and then we'll have plus theta minus 2 sum of y. Okay, and we'll set this equal to 0 for our maximum likelihood estimate. Okay, all right, so can we solve for our maximum likelihood estimate? I think so. So minus n alpha over theta plus 1 over theta squared sum of yi is equal to 0. So therefore, theta hat, what does that equal? You have n alpha, and it'll be 1 on n alpha sum of yi, okay? Or you can write that as 1 on alpha y bar, right? Okay. All right. Okay. So I think that's pretty much all good, hopefully. Okay. All right. So the next step is we're going to find the expected value and variance of theta hat. Okay. Let's see where we're going with this. Yeah, we're going to find the expected value of theta hats. I'm going to show it's consistent, and we're going to find the minimal sufficient statistic for theta. And I suppose we're going to end up finding if it's unbiased, right? Is that what we're going to do? Okay, I think something related to that. Okay. All right, so let's go to the next step here. Okay, and we're going to now find the expected value and the variance of theta hat. Okay. So part B, expected value of theta hat is equal to the expected value of 1 on alpha y bar. Okay. Now, in this example here, 1 on alpha is a constant. So this is 1 on alpha, expected value of y bar. Okay, now we should know. Okay. We should know the following. Okay. If y is distributed gamma alpha theta, then we have the following results. The expectation of y is equal to alpha theta, and the variance of y is equal to alpha plus 1 theta squared. Okay, so you can usually look these up in your table of distributions. Okay, all right. Hang on, not quite. Alpha theta squared. My bad. Okay, so this is what you'll need. Okay, I can prove that in a second. Okay, but for now, I think that we can all accept this. I don't know if I'll be able to prove that actually, because it's been a long time since I've tried to do that. Okay, but you can take these as given facts. All right. So therefore, we can now conclude. Okay, we can now conclude that the expected value of theta hat is equal to 1 on alpha times 1 on n, the expected value of y. No, sorry. 1 on n, and then you have n times the expected value of y, don't you? Okay, which gives you 1 on alpha times alpha theta, which is equal to theta. Okay, so you can actually say here that since the expected value of theta hat is equal to theta, that means that theta hat MLE is unbiased. That's a very nice result. Okay, it's unbiased, all right? Okay. All right, let's have a look at I just realized I made a mistake here. No, that's correct. No, sorry. That's correct. That's correct. Okay. All right. So let's go on to the next step, which is to look at the variance. Okay. So what is the variance of theta hat? Well, the variance of theta hat is equal to the variance of 1 over alpha y bar, which is equal to 1 over alpha squared, the variance of y bar, which is 1 over alpha squared times 1 over n squared times n, the variance of y. Okay. So therefore, the variance of theta hat is equal to 1 over alpha squared times 1 over n squared times n times alpha theta squared. Okay. All right. So what does that work out to be? That's going to work out to be 1 over n alpha, and you have theta squared. So it's theta squared over n alpha. Okay. All right. This leads really well to the next part because it asks us whether theta hat is consistent for theta. And this is an easy question because the answer is yes, right? Why is it? Because 1, the expected value of theta hat is equal to theta. In other words, it's unbiased. Okay. And secondly, the variance of theta hat, which is equal to theta squared over n alpha, goes to 0 as n goes to infinity. Okay. So with these two conditions, by mean square convergence, okay, theta hat is consistent for theta. Okay. All right. Are we all happy with that so far? Any questions about that? I don't think that that any of this is new for you guys. Hopefully not. All right. Let's go through the minimal statistic. Okay, so to get the minimal statistic, let me just copy the likelihood here. Okay, and we'll show how we can figure out the minimal statistic, the minimal sufficient statistic, by just having a look at the likelihood here. Okay, so this is going to be part D, right? We're trying to find a minimal sufficient statistic for theta. Okay. Now, there's actually two ways of doing this question, right? But before I do it this way, okay, I want to do it a different way, okay? And this might make sense in just a second. Actually, I probably shouldn't have done this because this is going to be a very technical way, okay? But before I go through the technical way, I want to just talk about what this means so that you're clear about what we mean when we say something is sufficient, okay? Let's just have a look at the formula for theta hat MLE, okay? Theta hat is equal to 1 over n alpha times the sum of yi. Okay, so based on this alone, you can say that therefore the sum of yi is sufficient for theta hat MLE. Okay, that should be intuitive, right? Why is that intuitive? Because if we know this sum right here, okay, we can calculate theta hat MLE with no further information. Okay, no further information on y. Okay. This right here, that's the definition of sufficient. Okay. And just look at the formula of this guy. I think it's fairly clear that the sum of y is sufficient, right? Because if you know the sum of y, you can calculate that maximum likelihood estimator without knowing anything else at all. Okay. So intuitively, right, before we even use factorization on the likelihood, okay, intuitively, that is going to be sufficient. All right. Okay, good. Now, I realize I copied the log likelihood. So let me go back and copy the likelihood. Okay. This is the likelihood. Okay. Now let's do this, but try to do it formally. Okay. So this is formally using the what do you call it? Using the factorization approach. Okay. Okay. So this is your likelihood here. All right. So let's have a look at this likelihood and see what we have. Okay. This part here doesn't depend on y. Okay. This part here doesn't depend on theta. Okay. So really it's a constant. Okay. Now this part here depends on y only through the sum of y. Okay. Now let me talk about why this is important. Okay. Why this will lead to how we can conclude from this that the sum of y is sufficient. Okay. How can we conclude from this that the sum of y is sufficient? Okay. Well, we see that we can only have three types of objects. Okay. We can, and what these three types of objects are going to be clear when we take this and change it into a log likelihood. Okay. So let me change this into a log likelihood and then you'll see what I mean. Okay. What do we have here? We have minus n times the log of gamma alpha minus n alpha times the log of theta. This becomes plus alpha minus 1, the sum of the log of yi, minus 1 over theta, the sum of yi. Okay? Now, this part here, that derivative of that, okay? So this is what happens when you have the derivative, okay, with respect to theta, of course. That's just going to be 0. And this is just going to be 0 because they're both constants, right? So they don't even matter, right, is the point that I'm trying to make, okay? So we can already agree that this entire thing right here, this entire thing, that doesn't really matter, okay? Because it doesn't depend on theta, it doesn't have any impact, this term right here, because it doesn't depend on theta, it doesn't have any impact on the estimate of theta, right? It's not relevant for calculating theta. So it doesn't matter, okay? This part right here, okay, that's not constant because it does depend on theta, but y doesn't enter that, right? So there's no y here. Okay, so again, that's not relevant to what we're talking about, right? So we can see here that this derivative just goes to 0. Okay. This derivative here just goes to 0. Okay. This derivative here goes to something which doesn't have y. Okay. And this right here, what that means is that if you replace this sum of yi with some other thing, let's say you replace this with f of yi, okay, then you can see that therefore the first order condition only depends on yi through f of yi, right? Why? Because this is the only place where yi will enter into the calculation of that first order condition. Okay, so therefore we can say, right, the conclusion here is that we can say that by factorization, right, and you don't have to do all this, right? This is just to show you why factorization works, right? But you could have shown this many steps ago, right? By factorization, okay, the sum of yi is minimally sufficient because you can't reduce that anymore, okay? Okay, you can't make that any simpler, okay, for theta hat, okay? All right. Okay. All right. Let's have a look at the last question. This is going to be really hard. I don't think that we're going to have enough time to do this last question here, which is we're asked to, given this sufficient statistic, and n equals 5 and alpha equals 2, construct a 90% CI for theta. How would you do that? That is going to be extremely, extremely difficult. Okay. I'm just going to say that the general idea here, I think, what you have to do is, yeah, I wouldn't even have any idea how you would approach a question like this. I think that what you would have to do here is you would have to look at the moment generating function of the sufficient statistic, okay? And once you do that, what you'll be able to do is then you can invert that moment generating function to figure out that that sufficient statistic is actually gamma distributed, okay? So what you'll find is that it's gamma distributed, and therefore, let me just write this down for a second here. Let me write that down here. So I'll give you a basic gist, okay? This isn't actually as difficult as I thought. Once I started thinking about it, I think I have an idea of how to do this. But this is actually quite hard. Okay, so we need to know, okay, what is the distribution of this sum right here, okay, of our sufficient statistic, okay? Because theta hat is equal to 1 over n alpha times that sum, okay? Where n is equal to 5 and alpha is equal to 2, okay? So in other words, if we know the distribution of this sum, we can figure out the distribution of theta hat, okay? Now, the way that we're going to do this, how would we do this? Okay. I'm going to say let u, okay, be the sum, okay? So let u of y be the sum of y, okay? Now, what we're interested in doing is finding what is the moment generating function of u, okay? Which is the expectation here of e to the t times u, okay? And how can we do that? U is a function of y. So we can do something like this. Okay, this is a sum of y. So you can do this. Theta alpha to the n. Expectation. Ty, y alpha minus 1. Exponential of minus y over theta dy. Okay. So with a little bit of simplification, we can see that we have the following. We have y alpha minus 1, and we have the exponential of minus, what is this? Minus 1 over theta minus t yi dy. Okay. What can we do from here? Well, this is a gamma function, right? So therefore, we can say the following. Okay. I'm just going to say gamma of alpha here, and then we have the following. Okie dokie, and therefore, by the property of the gamma function, this is conveniently equal to gamma, no, conveniently equal to 1 over theta minus t to the power of minus alpha. Okay, this is this property of the gamma function. Okay. Distribution. Okay. How did I get that? Because it has to integrate to 1. So you see here, right? How did I get that? I'll show you how I get that. In general, okay, you have this sort of relationship right here. Okay, you have the integral of 1 over gamma alpha, theta alpha, yi to the alpha minus 1, exponential of minus yi over theta. Okay. Theta to the, is that right? Let me just check. Yep. This is equal to 1, okay? Because it's a probability density function, all right? So therefore we can say, right, that the integral of 1 over this is just equal to theta alpha, okay? And in this case right here, you have, I suppose, this theta, okay, is just this, right? Does that make sense to everybody? Can you give me a yes or no if that makes sense, right? So that's why we're able to go from this step right here down to this step here, okay? You can think of this theta as just this entire quantity here, okay? So you can see that in here, okay? Right? So therefore we can make this jump because that has to integrate to this quantity right here, okay? Based on this, based on the area under a gamma distribution, a gamma density has to equal 1, okay? Anyway, the point here is that this is what we have, okay? So we have the moment generating function as being the following, okay? So 1 over gamma alpha, theta alpha to the n, okay? Then product of gamma alpha 1 over theta minus t to the minus alpha, okay? All right, so where does that lead us? Well, we can see here already that this is going to cancel out with this. And we have 1 over theta alpha n. And then this one here is going to be 1 on theta minus t to the power of minus n alpha, or alpha n, I suppose. Okay. So what can we do here? Well, we can have multiply through by theta to the alpha n. Okay, so we have the following. Theta times 1 over theta minus t minus alpha n. Okay, so therefore, mu of t 1 minus theta t to the power of minus n alpha. Okay. Okay. So you can recognize here, okay, the moment generating function of a gamma distribution. Okay, this is the moment generating function of a gamma distribution. All right. Okay, so what can we do from here? So what we can do from here is we can see, okay, that because, where is our original parameters? N is equal to 5 and alpha is equal to 2. Okay, we have the following mu. Okay, minus 2n if you substitute alpha in. Okay, so this right here is actually specifically the moment generating function of a chi-squared distribution with 2n degrees of freedom. Okay, so what can we do here? Well, from here we can say therefore the sum, okay, is going to be, and if this sum has, whoops, n is 10, this sum right here is going to be chi-squared 20 degrees of freedom. Actually, no, 10 degrees of freedom because n is 5. Okay. So therefore, theta hat, which is 1 over n alpha, so 2 times 5, times this sum right here, that's just going to be distributed 1 on 10 times the chi-square 10. Okay. All right. So I am happy with that. Hang on. No. This has to be 2 times 2n because chi-square is gamma 2. No, sorry, chi-square is gamma 2, not gamma 1. This should be 20. And this should be 20 here. Okay. All right. I think from there, that's straightforward. All you have to do is you just have to find the critical values from the chi-squared, and then you can do your CI. Okay. So you need to find critical values. Okay. Critical values. And from the critical values, you can get a CI for theta hat. Okay. Or for theta given theta hat. Okay. For theta. Okay. That's the general gist of how to do that. Okay. All right. What do you guys reckon? I think that's all pretty clear, hopefully. Okay. Do you guys have any questions or anything you wanted to have a chat to me about before we finish up for today? I think this is done. So yeah, this is basically done here. So there's just a hand-in exercise that you guys can do and get submitted to me. Okay. If you have any other questions, let me know. Otherwise, we can finish up. Do you guys have anything you wanted to ask me? No, I think everyone's happy. Are you guys alive out there? No? Not alive? No, not really. Okay. All right, guys. Well, I think we can finish off here. You guys can go and enjoy the rest of your day. Okay. And I'll see you guys again next week. All right. All right. See you later. Bye-bye. Thank you.